Hi everyone, and welcome to this tutorial. Today, we're diving into Jacobians, a key mathematical concept that plays a vital role in neural networks, optimization, and machine learning. Let's break it down step by step so it's easy to understand. Jacobians are used for vector-valued functions. Think of a function that takes multiple inputs and outputs multiple values. For example, in a neural network, you might have multiple features as input and multiple predictions as output. The Jacobian organizes all the partial derivatives between these inputs and outputs into a matrix. Mathematically, if your function maps from Rn to Rm, the Jacobian matrix captures how each output depends on each input. Here's the formal definition. The Jacobian matrix J of a function is written as shown. It's essentially a table of all first-order derivatives. Each row corresponds to one output, and each column corresponds to one input. Let's consider a vector function of a variable x, which is defined as follows. The function f of x is a column vector where the first entry is the square of the first component of x plus the second component of x. The second entry is 2 times the first component of x plus the sign of the second component of x. The input x is also a column vector, with 2 components, x1 and x2. To compute the Jacobian of this function, we organize all the partial derivatives into a matrix. Each entry in this matrix shows how one output changes with respect to one input. This matrix helps us understand how small changes in the inputs affect the outputs. The Jacobian matrix for this function is a 2 by 2 matrix. In the first row, the first entry is the derivative of the first output with respect to the first input, and the second entry is the derivative of the first output with respect to the second input. In the second row, the first entry is the derivative of the second output with respect to the first input, and the second entry is the derivative of the second output with respect to the second input. Now, substituting the partial derivatives. The derivative of the first output with respect to the first input is 2 times the first input. The derivative of the first output with respect to the second input is 1. The derivative of the second output with respect to the first input is 2. The derivative of the second output with respect to the second input is the cosine of the second input. So, the Jacobian matrix becomes a 2 by 2 matrix where the first row contains 2 times the first input and 1, and the second row contains 2 and the cosine of the second input. This matrix captures the relationship between the input and output variables, giving us a map of how sensitive the outputs are to changes in the inputs. This is a critical concept in optimization, machine learning, and neural networks. Now that we've covered the definition and basic example of the Jacobian, let's see how it's applied in a neural network. Imagine a simple neural network with a single hidden layer. This network takes a 2-dimensional input, processes it through a hidden layer with 2 neurons, and outputs 2 values. The activation function we're using is ReLU. In this example, we'll calculate the Jacobian matrix to understand how the outputs of the network change with respect to its inputs. This is particularly useful for analyzing the transformations performed by the network and understanding its sensitivity to input changes. Here's how we can compute the Jacobian using TensorFlow. In this code, we define a simple neural network in TensorFlow with a hidden layer and ReLU activation. The Jacobian matrix is calculated using TensorFlow's gradient tape. The tape.Jacobian function computes how each output of the network depends on each input. By examining the Jacobian, we can see the network's sensitivity to changes in the input and better understand its transformations. This is particularly useful in debugging, optimizing, and improving the interpretability of your models. If you found this video helpful, please like, share, and subscribe to support the channel and stay updated with more informative and engaging content. Thank you so much for watching, and we'll see you in the next video.